Okay, we're now heading into a new section that deals with chemical equations and reactions that we built our equations upon, and understanding how those work. So we're taking kind of a quantum leap up to the next level. We're going to start off with something you probably have done before with mixed results for something, and some probably do not do it pretty well, and some really struggle with it. So I'm going to present to you this option here, not really an option, but this way of doing this, in that I want you to do it this way for the beginning until you get more comfortable with this, then you don't have to do it this way. But to start off with, the first two assignments must be done the way that I show you. Okay? And well, let's just say all the assignments for this, I shouldn't say this first two sections, the entire chapter. This is how I want you to balance equations. Now, when we say balance equations, which again is a term you've probably heard before, this is based upon an idea by John Galton called the law of conservation of mass. And basically what Mr. Dalton came up with was that in a system where a reaction is taking place, whatever the mass of the materials that you had before you started the reaction has to equal the mass of the material you had after the reaction. Okay? So basically we're going to look at mass in terms of the number of atoms. So let's take a look at what we call the synthesis of water. Water is hydrogen gas, and hydrogen gas is written below 2. It's found diatomic. That's what that means. And it's a gas, and this is called a phase, so we put G in phase for gas, in parentheses for gas phase. Plus oxygen is also a diatomic gas, so O2G, and it's going to create, it's going to create water. Water at room temperature, as we know it, is a liquid, so we use L. S is for solid. There is one phase called AQ, which is aqueous, which means it is a compound dissolved in water, so it's not really a liquid, but it's not a solid anymore, so we call it aqueous. And we'll get into that later on in this chapter. But what we're going to really key on here is the fact that the number of atoms of hydrogen and oxygen on the left side must equal the number of atoms of hydrogen and oxygen on the right side. Right now, that is not the case. So we're going to show this with a line separating the reactants, which is what we call the left side of this equation, because they are reacting together, reactants, and we're going to produce water. And so we call the right side of the equation the products. Now, the number of atoms of hydrogen must equal the number of atoms on the reactants, must equal the number of hydrogen atoms on the products. Well, what I'm going to do is I'm going to write down just a plain H here, a plain H here. I'm going to write down the number of atoms I have in both. I have 2 atoms here. I have 2 atoms here. So we say that hydrogen is balanced. We go to oxygen. Oxygen, we have 2 here. Oxygen, we have 1 here. Oxygen is not balanced, so we need to do something about this. Now, one of the things we cannot do is change the formula. We can't make this H2O2. That is no longer water. That is something called hydrogen peroxide, which will kill you if you drink it. It's like the old joke, 2 guys walk into a bar, and bartender goes up, the first guy says, "What do you want?" And the guy goes, "I'd like some H2O." You know, bartender rolls his eyes, he goes and gets a glass of water, puts it on. "Thank you, sir, thank you, thank you. And what would you like?" And that guy goes, "I want H2O too." And he died. So, we've got to fix this so we can change the amount of oxygen without changing the formula. And the way we do this is by using something called coefficients. Now, in algebra, coefficients were the numbers multiplied by the variable. So we had the monomial for x. The 4 is considered the coefficient of x. We're going to do the same thing here. We need to double the number of oxygens. And everything's based upon multiplication when you put a coefficient in front of a series of atoms that make up a compound. We want 2 oxygens, so we're going to have to put a 2 in front of that. So we're going to double everything that's in the water, which means, yes, we are going to get 2 oxygens, which is now balancing the oxygen over here, but now we double the number of hydrogens to 4. So now we go over here and say, okay, that's great, now I just screwed up the hydrogen. So what are we going to do about that? Well, obviously, we need to double the number of hydrogens here, get 4 over here, and we can very easily do that by putting a coefficient of 2 in front and 2 times 2 is 4. And this is now a balanced equation. So the synthesis of water requires twice as many molecules of hydrogen as it does oxygen to create water, which makes sense because the number of atoms is twice. All right, well, let's take a look at another. Let's take a look at the synthesis of ammonia. We got N2 gas plus H2 gas yields NH3 gas. Ammonia is NH3. This is, again, stuff we use in fertilizers. This nitrogen in the atmosphere is not reactable, so the plants cannot take nitrogen out of the atmosphere. So we have to put in some form of reactable nitrogen in the ground, and one of the most reactable forms is ammonia. So again, draw the line here to separate the reactants from the products. And we write down each element, nitrogen and hydrogen. Nitrogen and hydrogen. So we have the identical elements on both sides. Then we write down how many we have. So we have 2 nitrogens here, 2 hydrogens here, 1 nitrogen here, and 3 hydrogens here. Nothing is balanced at all. So we're going to start with the nitrogen here. We see that we need to double the number of nitrogens to balance what we have over here. So that means we have to double the entire molecule, that is 3. And when that happens, this becomes a 2 here. And this becomes a 6 here. Now I want to make it common. We can never put a coefficient in the middle of a compound. It has to go in front of the entire molecule, and everything behind it must be double, triple, quadruple, depending upon what the coefficient is that we put in there. All right, well now the nitrogen balanced, that's pretty nice. Now we got to get the hydrogen balanced, so that's a 6 there, that's a 2 there. That means we need to triple the number of hydrogens, and that is now a balanced equation. How about that? Okay, next one. Chromium plus fluorine, chromium is a solid, plus fluorine is a gas, and this creates chromium 3 fluoride, which is a solid. It's an ionic compound, so it's a solid. All right, so again, we identify the elements on both sides of the arrow. We'll draw a line between the arrow. We have chromium and fluorine on both sides. We have 1 chromium here, 2 fluorines here, 1 chromium here, and 3 fluorines here. All right, this is one of those scenarios that we ran into when we dealt with the naming of compounds and finding the formulas of compounds based upon their names. We have chromium's balanced, but we don't have the ability to get 2 and 3 to equal each other without doing something to both. All right, so we know the lowest number that 2 and 3 are going to is 6. That means we're going to need to double the fluorines here. But we can't just put a 2 in the middle there. That doesn't work. It's got to go in front of the compound. So we got to double all of that. So that becomes a 6 there, and that becomes the 2 there. Now we can put coefficient in front of both of these. If we want chlorine to become 2, we got to double the number of chlorines. And we want to make fluorine. Why? That's for instance. If I got to make the fluorine 6, then I got to put a 3 right there. And now I have a balanced equation where everything now has a coefficient. So this is the process that I want you to use for balanced equations throughout this chapter. And after this chapter, you can balance it any way you want. But you must show the line, you must show the elements, and how they were changed. All right? Your homework is going to be an attached homework assignment to your Google Classroom page. So do those 5 balanced equations. Have fun!